This is part 2 of section 1.6, polynomial and rational functions. We will be covering rational functions in part 2. The goal of this video is to define a rational function, discuss the short run and long run behavior of rationals, as well as define what an asymptote is. A rational function is a function that can be written as a ratio of two polynomials. As the input values approach a from the left side, taking on very small values close to a, the function values become very large in the negative direction. In other words, they approach negative infinity. We write as x approaches a from the left, that's how this negative sign, f of x approaches negative infinity. Alternatively, as we approach a from the right side, the function values become very large in the positive direction, approaching infinity. We write as x approaches a from the right, whenever you have a positive sign, f of x approaches positive infinity. This behavior creates what we call a vertical asymptote. An asymptote is a line that the graph approaches. In this case, the graph is approaching the vertical line x equals a as the inputs become close to a. Typically, these come from rationals where the rational function is undefined. Because rational functions have polynomials in their denominator, they have values at which the function is undefined, or where the denominator would be 0 and we cannot divide by 0. So that would visually create an asymptote, a vertical asymptote. Alternatively, for a horizontal asymptote, as the values of x approach infinity, so this time we're talking about the long run behavior as x gets really large to the left and the right, if the function approaches a value b, then that b becomes our horizontal asymptote. So symbolically, we would say as x approaches positive or negative infinity, the function values approach b. Based on this long run behavior, the graph, we can see that the function approaches b but never actually reaches b. It just levels off as the inputs become large. To determine the vertical asymptote algebraically, we will set the denominator of the rational function equal to 0 and find where the numerator is not 0. If the numerator and denominator share a common factor that divides out when they're factored, we call that a whole. And so the function is undefined at that whole. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. And so there's three cases. If the degree of the denominator is larger than the degree of the numerator, the rational function has a horizontal asymptote at y equals 0. If the degree of the denominator is less than the degree of the numerator, there's no horizontal asymptote. And if the degree of the denominator equals the degree of the numerator, the horizontal asymptote is found by taking the ratio of leading coefficients. We want to find the horizontal intercepts, the vertical intercept, the vertical asymptotes, and horizontal asymptotes for the rational function, and we will take a look at the graph of this once we found all of those key components. So as a reminder, the vertical intercepts come from where the function is evaluated at 0. So we evaluate f at 0. We can see when the function is evaluated at 0, the numerator is negative 15. The denominator is positive 15, and the output is negative 1. And so this has a vertical intercept at 0, negative 1. For a rational function, horizontal intercepts are going to come from where the numerator equals 0. For this function, we'll set 2x squared plus 7x minus 15 equal to 0, and we will factor to find the horizontal intercepts. We can see that this graph, this rational function, will have a horizontal intercept at negative 5, 0, and at positive 3 over 2, 0. Next, to find the horizontal asymptote, the vertical asymptote, we will find where the denominator equals 0. So we'll set our denominator 3x squared minus 14x plus 15 equal to 0, and we will factor. We can see that this graph will have a vertical asymptote at x equals 3 and x equals 5/3. To find the horizontal asymptote, we want to consider the degree of the numerator and the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is also 2, and so we want to take a ratio of the leading terms. And so we can see that the horizontal asymptote will occur at 2/3. Let's take a moment to look at the graph of this function. I will be using Desmos to look at the graph of this function. We can see that the graph has a vertical asymptote at 3 and 5/3. Those are blue and green dotted lines. and then it approaches in the long run the horizontal asymptote y equals 2/3. That's our dotted purple line. So you will never see the function cross a vertical asymptote, but it is okay if the function crosses a horizontal asymptote. It's just a guideline for what it's doing out towards infinity in the negative and positive direction along the x values. In our next video, we will cover exponential functions.